Hello, welcome back to the video series for Geographical Data Analysis, Geog 300 at WVU. We're continuing our exploration here of multivariate regression. And we saw the general idea of one dependent variable being predicted by many independent variables in the previous video. The output table that you will get, it will look very similar to what you get in the bivariate regression, but I'll put an example up here and have that go off of a series of, and I'll show you the differences. And what I'm doing is I'm stripping down the important information in that table for the most part. So we still have for the intercept, when we have, just to put some values there, still get our value or our coefficient of the intercept, that beta is 0, and its associated p-value. So I may have things like looking at many things at once. The per capita income of a county, the poverty rate for a county, and the percent with a high school degree as representing education for the county. Now we get a series of coefficients and a series of p-values, one for each variable. So here I have 3, and the dependent variable could be the health insurance rate or anything. So income is, okay, something that would be positively correlated with income. I figure health insurance rate probably would be. So we have a coefficient here and associated p-value. This p-value would tell us that income is significantly correlated with health insurance. That is, if I pick 0.05, that will show up, and I can say there is a relationship between this particular independent variable and the dependent. For poverty, yes, the coefficient is larger, but the poverty rate might range from 0 to 30% in a county, whereas the per capita income ranges from like 10,000 to, I don't know, 50,000. So, as we'll see shortly when we look at the exact interpretation, a larger valued coefficient may well not be significant, as is the case here. This particular p-value, it's above a threshold, and so we would say there's not really a relationship there. People under the poverty line, they may qualify for Medicaid, and therefore they still have health insurance, so it intuitively can make sense that this would not be significant. And education. This one is a positive relationship and is extremely significant. So it could be that people without a high school degree have a harder time getting jobs that provide health insurance. So this, in a way, is as much a factor, even more of the factor, so to speak, than income. So those are, so we can look at and have those relationships, all three independent variables. But the interpretation of the coefficient has changed some. So, whereas before the coefficient was pretty straightforward. If I increase the independent variable by 1 unit, whatever unit it is in, what is the effect on the dependent variable? What happens to it? Does it go up or down? By how much does it go up or down for each unit of the independent variable? Now, I have 3 independent variables. The name independent variable suggests we are assuming they behave independently of each other. That even though in reality, yes, education rate for a county is probably correlated with the income to a certain, at least small extent. Likewise, the income rate and or income per capita and the poverty rate. But for the purposes of regression, we assume that they behave and operate independently. There is a way to check that in the software. But we are assuming they are independent, and that means this coefficient. What happens to the health insurance rate if I increase the per capita income of a county by a single dollar? Why this is so low? A single dollar in the entire range of 40, 50, whatever, $1,000, small drop in the bucket. But a bunch of drops can add up over time, over many dollars, to a significant effect. But it's also what happens if I increase the per capita income by $1 while keeping the poverty rate the same, while keeping the high school graduation rate the same. So it's now the marginal effect. What happens if I increase that variable and only that independent variable while keeping everything else constant? So that would be the new interpretation of the coefficients. In a sense, it's not that different from bivariate. We just have to remember we're keeping everything else the same. The other main difference in what you would be seeing or looking at, you may have noticed in the software that you had, actually there were 2 r-squared values in there. There's not much difference in them in the bivariate setting, but there are 2 there. So we had the regular r-squared, and we still get the regular r-squared, and it's actually interpreted the exact same way. The amount of variation in health insurance that we can explain with our now 3 variables here. But people realize that if I just keep adding to this, and you put in everything in the kitchen sink into your regression equation, the term is actually called the kitchen sink regression if you do that. Put in everything in the kitchen sink, every single variable you add can only improve the r-squared. or keep it the same if it's absolutely useless as an independent variable. Because you'll never get yourself a worse prediction by adding more information. However, if you have a lot of variables that are not really significant, and you have a lot of ultimately useless information, because yes, you're putting a variable into your regression equation, and it boosts the R-squared just a tiny bit, but it's not really a significant predictor. And you do that over and over again, you can give yourself a pretty decent R-squared value, even if it doesn't really mean much of anything. So, people came up with this idea of the adjusted R-squared. So we're going to penalize the R-squared value, adjust it, by saying, because I know, even if there's no actual relationship, my R-squared is going to probably go up a little bit every time I add a variable. That means I should adjust it and take it down that little bit. Then I have a valid comparison, a valid look at being able to say, what happened to the adjusted R-squared when I added that variable? R-squared went up, but did the adjusted R-squared also go up? If it did, then okay, this may be an improvement. If the adjusted R-squared went down, then we can say, yeah, it may have helped a very tiny bit, but it's not necessarily worth including. And so therefore, that's the way we can interpret and use this penalty for having, in a sense, too many variables in our regression equation. So, and those are these coefficients, they're p-values. You would still see the R-squared possibly. You would definitely see the adjusted R-squared. The other thing that we saw some with the spatial regressions, we saw the AIC information criterion. Its interpretation hasn't changed from bivariate to multivariate regression. So that is what we will be working with and what we will be interpreting in multivariate regression. We have a coefficient for every independent variable and a p-value for every independent variable. We have the R-squared or adjusted R-squared now giving us the overall relationship. It still has its p-value. And it's possible for these p-values to not be significant, but for the overall effect of being able to collectively predict that dependent variable can still be significant. So now we can see a discrepancy between that R-squared p-value and the coefficients p-values. And as I have here, AIC, working with that, it has not changed. Low values are still representing the best possible model. So as always, if there are any questions, please feel free to ask in class or to send me an email. Thank you for watching. Have a good one.